For this project, we plan to run multiple simulations on various components of the UCI and Eater electric car. The design of the race car balances safety, weight, rigidity, and speed. The conducted simulations optimize the following components to reduce weight while keeping the driver safe under worst-case loading conditions. The brake rotor is a component on the car that undergoes constant thermal stress. The brake pads are attached to the rotors and through its applied pressures causes friction force which stops the vehicle. The first iteration resulted in extremely high temperatures, therefore there were high thermal stresses of 1,280 megapascals at the location of the brake pad, which yielded the part. To address this design issue, in the next iterations, more venting and surface area were added. Under the same boundary conditions, it showed improvement, lowering the thermal stresses to 334 megapascals. The added surface area helped with convection and heat distribution throughout the rotor.
The impact attenuator is mounted on the front of the car to absorb energy in the event of a collision. For the purposes of a race car, we want the attenuator to yield for large decelerations above 3 Gs, but not for small ones, all while being as light as possible. It is mounted with a strong adhesive to a plate that has a much higher stiffness, and so will be modeled with a fixed geometry on the mounting face. The first iteration was overbuilt, meeting the performance requirements, but was heavier than needed. Our second iteration reduced weight by 30% while still performing as needed, but upon removing more weight, we saw that the impact attenuator would yield under too little acceleration.
The control arm is designed to connect each wheel to the chassis of the car. Control arms are used to transfer the force exerted on the wheels into the shocks to smoothen the ride and keep all 4 wheels on the ground. There were a total of 4 simulations conducted, 2 static studies and 2 buckling studies. The simulations were designed to mimic the effects of both braking and cornering on the lower front control arms. The material is AISI 1020 cold rolled steel that will transfer longitudinal forces from the road, cornering forces generated when undergoing a turn, and vertical forces from suspending the chassis in the air through both the shock and the tire.
The chassis is the main structure of the vehicle. This part is heavily triangulated, which helps to direct forces toward the nodes, which are welded meetings of steel tubing with very high strength. The intent of this design was to reduce stress built up throughout the chassis. I ran several simulations to determine optimal locations for added triangulating members. This also helped me make a change to the material. The presented cases show an 1150 pound force, which models a 500 pound object impacting the chassis at 25 miles per hour. The first iteration yielded when considering axial and bending stress. The second iteration included 3 new triangulated members, which drastically reduced axial and bending stress buildup and deflection. The third adds 1 more member that further reduces stress and deflection, as well as a material change that showed improved results.
The brake pedal translates force applied by the driver into hydraulic pressure generated by the master cylinders. In emergency stop, a maximum normal force of 500 pounds is applied to the fully extended pedal. This is modeled as being rigidly fixed at both ends with applied load in between. The pedal is a thin model, loaded and restrained in plane, and can be modeled with 2D simplification plane stress elements. A nonlinear static analysis will result in the most representative analysis, as the fixed pedal stiffness may increase as it is deformed. The first iteration does not yield and has an FOS of 1.98. To reduce weight, the diameters of the material cutouts were increased by 37.5%. This resulted in a 23.5% decrease in weight, but a FOS of 0.752. To account for these discrepancies, the cutouts were increased by 20% and were slotted. This resulted in a 28% decrease in weight and a FOS of 1.17.
The chassis tabs are used to attach various components to the car. For these simulations, I am focusing on the tabs that mount the battery box. This load is approximated as a 110 pound force. I loaded the tab in 2 different ways, with the force parallel to the face of the tab and normal to the face of the tab. The normal force was more significant. For the normal force, the first iteration yielded. For the second iteration, I made the tab thicker and the part did not yield, but the tab was heavier. For the third iteration, I added a wedge to the tab and the part did not yield and it was not as heavy as the second iteration.